The Big Bang Theory has faced new challenges with the latest discoveries made by the James Webb Space Telescope, which has provided groundbreaking insights that could reshape our understanding of the universe. A recent image captured by this telescope has generated significant discussion among experts, presenting compelling arguments that have surprised the scientific community and resolved long-standing debates about the nature of the cosmos. This visually stunning discovery is not just another astronomical observation, but has the potential to transform our perception of the universe. The latest image taken by the James Webb Space Telescope challenges some of our most fundamental assumptions, particularly regarding the age of the universe and its rate of expansion. These questions have puzzled scientists for generations, leading to extensive research and various hypotheses in search of definitive answers. Cosmologists dedicate their work to understanding how the universe originated, how it functions, how it has evolved over time, and ultimately, how it will end. Over the last several decades, there have been significant advancements in this field. The Big Bang Theory, which remains the most widely accepted explanation for the origins of the universe, suggests that the cosmos has been expanding for approximately 13.8 billion years, beginning from an extremely hot and dense state. A key factor in measuring this expansion is the Hubble constant, which determines the rate at which the universe is growing. However, calculating this constant is far from straightforward, as two primary methods, local measurements and observations, of the early universe often yield different results. Scientists rely on specific celestial objects, such as stars and Type Ia supernovae, to serve as standard candles due to their predictable brightness. By measuring their distances, astronomers attempt to determine the Hubble constant. The expansion of the universe does not occur at a uniform rate, making it even more challenging to pinpoint an exact value. One approach involves studying the early universe through observations of the cosmic microwave background, CMB radiation, a remnant from when the universe was only 380,000 years old. First detected in the 1960s, the CMB provides valuable insights into the universe's age and expansion rate by analyzing tiny fluctuations in its temperature and polarization. However, a significant problem arises. These early universe measurements do not match local measurements. Data collected from nearby galaxies suggest that the universe is expanding faster than what CMB readings indicate. Scientists have been working tirelessly to resolve this discrepancy, as it suggests either an incomplete understanding of fundamental physics or potential errors in one or both methodologies. With the powerful capabilities of the James Webb Space Telescope, scientists can now peer deeper into space than ever before, revealing celestial objects and phenomena that were once thought impossible to detect. Researchers initially hoped that the telescope's data would help refine calculations of the Hubble constant. Yet the first set of findings have introduced unexpected inconsistencies. This new information challenges existing models and forces scientists to reconsider what they know about the nature of space. There is growing speculation that these discoveries could lead to the identification of previously unknown particles or forces, or even a re-evaluation of the concept of dark energy, an enigmatic force responsible for accelerating the universe's expansion. Scientific understanding of space has continuously evolved with each new discovery. For example, when the cosmic microwave background radiation was detected in 1965, it provided strong evidence for the Big Bang, challenging previous assumptions that the universe would expand indefinitely at a constant rate. Then, in the late 1990s, observations revealed that the expansion of the universe was actually accelerating due to dark energy, a revelation that reshaped our understanding of cosmology. Every new finding forces scientists to test whether it aligns with existing theories or if it necessitates a new framework to explain the universe's behavior. Without these challenges, the field of cosmology would stagnate rather than progress. One of the most intriguing aspects of the current cosmological debate is the concept of Hubble tension, which refers to the discrepancy between different measurements of the universe's expansion rate. This issue is closely linked to the distribution of matter in space, as variations in matter density across different regions help shape the large-scale structure of the universe. Some areas are densely populated with galaxies, while others are relatively empty. Scientists use various methods to study this distribution, including gravitational lensing, a phenomenon in which massive objects, such as galaxy clusters, bend and magnify light from more distant celestial bodies. This effect allows researchers to infer the presence of dark matter, a mysterious substance that does not emit light but influences the gravitational structure of the universe. Further analysis of the cosmic microwave background provides another avenue for understanding these cosmic irregularities. The light from the CMB has traveled for about 13.8 billion years, carrying information from the early universe. However, there is an unresolved issue. The large-scale distribution of matter observed today does not match the uniformity suggested by CMB data. This discrepancy implies that there may be unknown factors influencing the structure of the universe. The non-uniform distribution of gravity suggests that the universe was more homogeneous in its early stages than what is currently observed through gravitational lensing. This inconsistency has led scientists to revisit theories about dark matter and its role in cosmic evolution. A research team led by Ryan and his colleagues utilized the James Webb Space Telescope to investigate whether measurement errors in previous telescopic observations could be responsible for these inconsistencies. Their findings, however, only confirmed the discrepancies, reinforcing the notion that there may be a fundamental flaw in our current understanding of the cosmos. In an interview with an astronomical magazine in the United States, Ryan expressed concern that somewhere between these observations lies a critical gap in knowledge. The James Webb Space Telescope's ability to capture incredibly sharp and detailed images has enabled astronomers to study cosmic distances with unprecedented precision. Yet instead of resolving uncertainties, it has introduced new questions about the nature of dark matter and dark energy. Both dark matter and dark energy remain among the greatest mysteries in physics. They are believed to comprise a significant portion of the universe, yet their true nature continues to elude scientists. While black holes have traditionally been considered the most likely explanation for certain gravitational anomalies, recent findings suggest that dark matter and dark energy might play a far more complex role in shaping the universe than previously thought. The growing body of evidence indicates that our current models may need to be revised, as they do not fully account for the intricate interactions governing cosmic expansion. The revelations brought forth by the James Webb Space Telescope emphasize the ever-evolving nature of scientific exploration. Each discovery presents new challenges and prompts scientists to refine their theories, leading to deeper insights into the universe. The unresolved discrepancies in cosmological measurements highlight the need for continued research and more sophisticated observational techniques. As technology advances and telescopes become even more powerful, the hope remains that these mysteries will eventually be unraveled. Until then, the pursuit of understanding the fundamental forces that shape our universe remains one of the most exciting and intellectually stimulating endeavors in modern science. The discoveries made by the James Webb Space Telescope, JWST, have provided some of the most striking challenges to our current understanding of the universe. While astronomers initially expected the telescope's observations to help resolve long-standing cosmological debates, its findings have instead introduced new uncertainties, forcing a re-evaluation of key aspects of the Big Bang theory. The debate over the universe's expansion, the role of dark matter and dark energy, and the inconsistencies in current measurements has led scientists to reconsider what they thought they knew about the cosmos. With its ability to observe distant galaxies with unprecedented clarity, the JWST has revealed new celestial structures and data that do not fully align with prior models, suggesting that something fundamental may be missing from our theories. One of the biggest unresolved questions in cosmology is the rate at which the universe is expanding. The Hubble constant, a key value used to measure this expansion, has been calculated using two different methods, one based on the cosmic microwave background, CMB radiation from the early universe, and the other relying on local measurements of stars and galaxies. However, these two approaches produce conflicting results, a problem known as Hubble tension. If the universe were expanding at a rate suggested by early universe data, it should appear slightly different when observed through local measurements. The fact that these two methods yield inconsistent numbers suggests that there might be unknown physics at play, or that existing models of cosmic expansion need revision. The JWST was expected to help resolve this issue by offering more precise measurements of distant objects, but instead it has deepened the mystery.